Welcome. Before we begin, we would like to acknowledge those who helped make this research project possible. This project was funded through a grant from the Department of Homeland Security, Federal Emergency Management Agency's Assistance to and Skin Burn Assessments.
On how we can be better. Why we vent, and when, where, and why do we search based on what we feel is survivable space.
What is most impressive about out here is just the overall coordination it takes to make it all happen.
It's very important for us to be able to have fire service partners, such as the Sydney Fire Department, to be able to come out into the field and do these tests.
Without the support of the Beaver Creek Township Fire Department, we'd never be able to accomplish such great work for the fire service.
Ultimately, without their partnership, we aren't able to get these structures. We can't do it on our own.
I think it's been great for our folks to see how deep the research can go.
As a firefighter, we study you well, we look into their experiments, and it drives what we do, so to actually get to participate in their experiments.
In this course, we will examine the results of the experiments in the context of fireground operations. It is our goal to improve your knowledge of fire dynamics and the impact of your tactics through a better understanding of how suppression and ventilation are coordinated during fires in single-family residential structures. Specifically, at the conclusion of this course, you will be able to describe the basic principles of fire dynamics and the factors that influence fire spread and fire behavior in single-family homes, and describe the impact of coordinated ventilation and suppression tactics on fire dynamics, firefighter safety, and occupant tenability on the single-family residential fire. As you work through the course content, remember that this information is presented to give you some things, and the appropriate response to each incident depends on as you consider the information situation. This course is divided into sections, as shown here. You can use this course map to navigate the content and track your progress. The tragic loss of civilian and firefighter lives in residential structure fires continue around. The changing dynamics of residential fires due to the changes in construction materials, building contents, and building size and geometry over the past 50 years add complexity to the influence of bath interior finishing and synthetic fuels. Click to learn more about the modern fire environment, or click next to continue. Data collected by the U.S. Census Bureau indicated that from 1973 to 2017, the average size of a single-family home in the U.S. increased from 1,600 square feet to approximately 2,500. Ventilation is a frequently used firefighting tactic and involves removing smoke and heat from the structure concentrations, can potentially and the ventilation opening. While no known studies compile statistics on ventilation-induced fire injuries and fatalities, a quick scan of NIOSH line-of-duty death reports provides several examples of the impact of improper ventilation on firefighter safety in a residential fire environment. Click to read more about these specific examples, or click next to continue. Traditionally, fire behavior is explained using this fire development curve. This ideal curve is best suited for describing stage and decay stage, and the fire goes into the decay stage. This graph is a more accurate representation of fire development in a compartment. In a it's clear that current ventilation practices and changes will take a closer fire department intervention. To understand the impact of fire department interventions on the effectiveness, as such, diagram were well characterized, that serves as the basis for this work. Use this menu to explore the results of our previous work and track your progress through the rest of this module. The horizontal ventilation study emphasized the change in fire dynamics resulting from predominantly synthetic fuel loads, specifically the increased likelihood of the fire department encountering ventilation-limited fire conditions upon arrival. This study also highlighted the need for the fire service to understand flow paths within structures, the impact of closed doors on preserving occupant tenability, and tactical measures to limit the amount of available oxygen in trade. The experiments conducted as part of the vertical ventilation study reinforced some of the key takeaways from the horizontal ventilation study, such as the increased density of synthetic fuels, the importance of understanding flow paths, controlling the access door, and coordinating activities on the fire ground. One of the new discoveries was the importance of hole placement during vertical ventilation. For a coordinated attack, a vertical ventilation opening placed over the seat of the fire is more effective than an opening located remotely. Additionally, this study brought to light the concept of softening the target with exterior water application during suppression operations. Exterior or the interior has the most significant impact on occupant tenability and firefighter safety. The positive pressure ventilation experiments reaffirmed the impact of closed doors and exterior water application on occupant tenability and firefighter safety. New findings provided guidance for using positive pressure fans for ventilation, including the size of ventilation openings, inlet-to-outlet ratio, and the importance of controlling the flow path. The effectiveness of positive pressure attack or ventilation measures is dependent on the exhaust opening size and location. The opening must be of adequate size and should be located in the fire compartment. Additionally, ventilation openings made in compartments remote from the fire may draw and extend the fire into previously uninvolved. Use this menu to review the key findings of the fire attack study. A solid understanding of air entrainment and water distribution is critical to understanding the impact of suppression operations on the fire ground. Click to learn more. Before discussing the impact of air entrainment on suppression operations, we must first understand how a water droplet moving through space entrains air. As water leaves the end of the nozzle, the momentum of the hose stream propels the droplets forward. As the droplets impact the air head, an area of high pressure is created. In the wake of the droplets, and carried forward with the droplet. If we apply these same concepts to hose streams, the impact of air entrainment should be clear. Suppose that you are holding a straight or a solid stream in a fixed position at the start of the hallway. You are flowing water down the hallway without manipulating the stream in any pattern. In this case, you are entraining. If we change from a straight stream to a fog stream, manipulate that fog stream in an O pattern, we can expect to see air entrainment in excess of 15,000 CFM. How we manipulate the hose stream inside a structure can change the amount of air that is in, so they can. It is essential to understand these concepts when applying these hose streams within a structure. Now, let's look at water mapping, or how water is distributed within a compartment. If we apply a hose stream perpendicular to a surface, the water will radiate 360 degrees. We often picture that as a stream applied straight ahead towards a wall, but let's imagine that stream applied to the ceiling. The steeper the angle into the compartment, the more the water will radiate outwards in all directions. But let's imagine that stream applied to the ceiling, and the water radiates outward. Once the water has coated the ceiling surface and reaches the sidewalls, depending on the obstructions that may or may not be present. This water application method nearly simultaneously coats all surfaces within a compartment and is effective in fire suppression. Now, let's apply the hose stream into the fire compartment from the hallway or through a window from the exterior. In these cases, you will want to employ a steep stream initially to coat all interior surfaces and rapidly reduce temperatures inside the fire compartment. The drop in temperature causes the fire gases to contract. A follow-up water application will be required. For example, suppose the firefighters are located on the same level as the fire. In that case, the nozzle can be inserted into the window and additional water can be applied to the remaining burning fuels. Suppose the firefighters are located on a different level than the fire. In that case, the hose stream can be deflected off the window header to achieve additional distribution, followed by entry into the compartment for final extinguishment. Now let's look at what we've learned about exterior water application. As we now know from studying hose stream mechanics, properly mapping the water inside a fire compartment is the critical factor in the success of extinguishment. This includes water applied from the exterior. An initial application of water into the fire compartment at a steep angle, center of the compartment, and all in training the least amount of air. We must also ensure that the window opening is not occluded with the hose stream. An occluded vent will prevent the opening from serving as a low-pressure vent for the exhaust of fire gases. Thus, the fire gases will be redirected to another outlet within the structure. In short, we need the most amount of water in the window with the least amount of air entrainment, and no matter what we do, we should not occlude the opening. We have seen the success of a flow and move approach of interior water application. This approach allows us to take advantage of maximum surface cooling. For example, an O pattern can essentially seal off the space ahead of the advancing hose line. This will prevent products of combustion from coming back over the firefighters while allowing the higher temperature, higher pressure gases behind the firefighters to vent out of the structure. This allows us to take advantage of air entrainment to draw fresh air in behind the advancing crew, improving conditions for potentially trapped occupants and fire crews inside the structure. Once the nozzle team has an idea of the location of the fire, attempts should be made to get water into the compartment as early as possible. This could include deflecting the hose stream off the door frame to the fire compartment. As the nozzle team reaches the threshold of the compartment, the same approach to that of exterior water application should be taken. An initial steep angle will coat all surfaces in the compartment. Once the fire is darkened down, the stream can be brought lower to the remaining burning fuels. After the fire is extinguished, the nozzle team should employ hydraulic ventilation out of any available opening in the fire compartment to aid in the smoke removal from the structure. Understanding the fundamentals of hose stream mechanics is vital to the success of fire suppression operations. This includes knowing when and how to utilize air entrainment to your advantage, understanding deflection methods to successfully move approach both on the exterior and suppression operations. A simple-to-reference summary of fire suppression conclusions is being applied from an off-plane position. Once the nozzle firefighter is on plane with the fire, better mapping can be achieved and a more effective knock fire compartment for base fire extinguishment. The prior research studies have shown little correlation between visible fire and smoke condition variables to say with certainty whether a space is survivable for a potentially trapped occupant based merely on the conditions visible from the exterior during a fireground size-up. Consideration should be given to how best to employ search, suppression, The fire attack study built on previous research on fire service ventilation and suppression tactics. The goal was to provide a comprehensive assessment of the impact of these firefighting tactics on chemical and thermal exposure to firefighters and potential occupants of the structure. Tactical considerations were developed from 3 sets of experiments, looking at air entrainment, water mapping, and bedroom fires in full-scale structures. These considerations provide data-driven insight into interior flow path. For more detailed information and discussion on the tactical considerations developed from the research, download the associated technical reports and check out our online training. This background review is intended to bring you up to speed on the relevant conclusions from previous research before and training courses. You hear it around the table in standard op very slow. Department working definition. Click next to continue. Let's take a moment to hear from a few of those tech panel members. As you heard, despite the complexities of the fireground and the many variables that contribute to the definition of coordination, there is some common ground. We can agree that a coordinated fire attack is based on a systematic approach. Coordination is understanding whether these actions can be performed. The National Fire Protection Association crews operable, enhance life safety. Armed with this understanding of fireground coordination and charged by the focus of the fire service technical by the fire location. Click Next to continue. The main control variables included the position of the initial application of water, the ventilation method, and whether that ventilation was performed before or after water was applied to the fire compartment. Although additional strategies were conducted during specific test scenarios.